This is part C for our unit on multiple regression. And in the previous section, I was talking about betas. I was talking about what betas are and how to interpret them. And now I'd like to take that a little bit further, and I want to compare the betas we get when we just do our regular regression equation and we do not do any kind of standardization, and compare that with a standardized beta, and then compare that with something we haven't talked about before, which is a partial correlation. And as we go along here, you will see that the difference between a standardized beta and a partial correlation is maybe a rather subtle difference. It has to do when in the process of calculation do you standardize. So with a standardized beta, what we will do is the very first step will be to turn everything into z-scores. We'll take all of our x variables and our y variable, our outcome, and we will turn everything to z-scores. We will standardize everything prior to analysis. In contrast with a partial correlation, we're first going to extract residuals out of our x variables and out of y, and then once we've extracted those residuals, we're going to standardize those. We'll turn our residuals into z-scores. And a standardized beta and a partial correlation are very similar. It's just a little different in terms of at what point do you standardize. So let's take a closer look at betas and compare them to standardized betas and partial correlations. So first, let's review what a beta is when you do multiple regression and you don't do any kind of standardization. This is what we've been talking about in the previous section, and I'm just going to review it again here. This slide is a slightly different way of depicting what we've been talking about, and I'm going to use this as a way to compare the beta with a standardized beta and a partial correlation. So again, say I'm doing multiple regression and maybe I have two predictors. Maybe I have x1 and x2, and I'm going to use my two x variables to predict y. For the sake of this example, let's say we're going to focus on the beta for x1, and I want to know what is the beta for x1 controlling for x2. So if I get the beta for x1, then x2 is my control variable. Or we could have done an example where we used x2 was our target variable and x1 was the control. We could do it either way. The beta for x1 gives me the effect of x1 controlling for x2. The beta for x2 gives me the effect of x2 controlling for x1. So this slide here is looking at the beta for x1 controlling for my control variable. And I guess I've switched my figures here. The last section I had, the vampire bunny thing was my control variable, and now I've got this big hungry frog is now my visual figure for the control variable. So we have an x variable, and we're going to extract, the control variable is going to extract everything it can out of x, and then I have a y variable, an outcome, and the control variable is going to extract everything it can out of my y variable. And that's what we talked about in our previous section, how we can use one variable to extract variance out of another. And so if I have my x1, my predictor here, x1, part of that x1 is going to be the stuff that's explained by the control variable. That's the purple area here. That's the stuff, in this case, my control variable is this big, hungry, wide-mouthed frog, and my control variable comes along and eats up everything it can out of x1, and the yellow stuff is all the residual, the stuff that's left over that the frog could not eat up. That is the stuff that the control variable could not explain. And so I've divided my x variable into the purple area, which is the stuff that could be explained by the control variable, the stuff that my big hungry frog could eat up and munch and chew, and now that part's gone. And then the yellow area is the residual, the stuff that's left over, the stuff that could not be explained by my control variable. And then the control variable does the same thing for y. The control variable comes along and explains everything it can explain. My big hungry frog takes a big bite out of y, chews up everything it can digest, and all the leftovers, this yellow area, is the stuff that's left over that could not be explained. And so now I have new scores. So I have everybody's new score on x1, which is your score on x1 with a control variable extracted out of it. And I could call that your uniqueness on x1. It's your unique score on x1, the part of x1 that's unique to x1 and can't be explained by the control. and everyone has a uniqueness on y. That's your new score on y with the control variable extracted out of it. And then we'll simply do a simple regression equation where I use that uniqueness of x1, that residual for x1 with the control variable extracted out, and I use that uniqueness of x1 to predict the uniqueness of y, that part of y that's left over after the control variable is extracted out. And when I do that, I get a beta weight for how well x1, the residual of x1, predicts the residual of y. That is, what's the expected increase in the residual of y given a 1 unit increase in the residual of x will be the beta for x1 in that simple regression equation. And that beta for x1 is identical to the beta I would get if I was doing multiple regression using both x1 and x2 to predict y. And if I use the standard matrix algebra equations for calculating the beta for x1 in that multiple regression equation, what I would get is identical to what I would get here if I extract my control variable at x1 and I extract my control variable out of y and then use the uniqueness or the residual of x1 to predict the residual of y and get that beta from that simple regression equation. Now, here is an example that I can use as we go along here to compare a regular beta that we would get from a multiple regression equation with no standardization and compare that to a standardized beta and a partial correlation. So say I did a study and I wanted to understand what makes some people more influential than others. Maybe some people are big influencers, and if they have ideas and plans that people want to follow and do the things they suggest, and maybe other people are less influential. So I want to know what makes people influential. So say I do a study and I get a sample of 552 people, and I give them all a questionnaire measuring the extent to which they're an influential person. That's my outcome variable, how much influence you have on other people. And for this study, I'm going to look at just two variables that might predict how influential someone is. The first is someone's income. Maybe people who have a higher socioeconomic status might be more influential than people with lower socioeconomic status. In other words, people that make more money might be more influential. And in my sample of 552 people, I collected information on, say, their annual income. And the average here was around $85,000 with a standard deviation of about $57,000, $58,000. So I got information on their income. And then I also thought maybe people are more influential if they smile more often. And so maybe as part of my study, I brought people into my lab and I had them interact with a Confederate, say for 10 minutes, with some kind of a casual conversation, and I video recorded those conversations and then just counted how many times did someone smile in that 10-minute period. And so I did that for all 552 people, and I have my smile score here, and the average person smiled an average of about 2.5 smiles in 10 minutes with a standard deviation of almost 1. So in this example, we can use how often a person smiled and a person's income to try to predict how influential they are. So here are the results from the hypothetical study with 552 people. And in the results here, I got an intercept of 38.55. The slope, beta 1 for income, the beta for income was 0.00007. And the second slope, beta 2, the beta for number of smiles, was 1.34. So consider this question. If we compare income and smiles, our two predictor variables, which of those two predictor variables had a bigger effect in predicting how influential a person was? Was income more important in predicting influence, or was smiles more important? Which of these had a bigger effect? Many years ago, I used to ask that question in classes, and then I stopped asking that question because every time I ask that question, just about everyone gets it wrong. So what do you think? Does income have a bigger effect or smiles? The answer that most people give is say, well, smiles has a bigger effect because the beta is bigger. 1.34 is certainly much, much bigger than 0.00007, and that is certainly true. But that doesn't mean that smiles has a bigger effect. Why is that? That's another question to consider. Why could it be that this effect 1.34 is actually not a bigger effect than 0.00007? The number's bigger. Why is it not a bigger effect? And the answer is because we're measuring income and smiles in different units. Recall that a beta tells you what's the predicted increase in Y given a 1 unit increase in X. Well, what is a 1 unit increase in income? That would be, for example, if you make $85,000 a year and your income goes up by $1. Well, that would be a pretty small increase. That's not much of an increase there. What about smiles? Well, there we measured smiles in 10 minutes, and the average person smiled only 2.5 times. So if someone went from, say, 2 to 3 smiles, given our scale, that would actually be a pretty big increase in the number of smiles. So a 1 unit increase in income is nowhere close to the same unit or same size as a 1 unit increase in smiles. We're measuring income and smiles in very different units. And that's one thing to keep in mind whenever you look at results from a multiple regression or any type of regression. Recall that if you do not standardize your variables, then you interpret X tells you what's the expected increase in Y given a 1 unit increase in X. And to understand what that beta means, you need to understand what units of X mean and what the units of Y mean, because you're measuring the effect in the units of X and Y. And if you don't know what those units mean, then you can't really interpret what the beta means. There are some areas of research where we investigate things where we look at variables that have meaningful units. And in those cases, oftentimes, the betas are meaningful to us. In psychology, though, in psychology and neuroscience research, we look at a lot of variables that can't be measured in meaningful units. For example, anxiety or depression or self-esteem or relationship satisfaction. These are all variables that we can measure, but when we measure them with what I would call arbitrary units. There's no official set unit for happiness or self-esteem or depression. So when we make scales, we measure these variables using arbitrary units. And when we measure things in arbitrary units, then the raw score betas really are difficult to interpret because we don't know what a 1 unit increase means. We don't know if a 1 unit increase means something big or something small. So we need to find a way to deal with this issue. And as we saw in our previous unit on simple regression, the standardized beta indeed solves this issue. Because if we turn everything into z-scores prior to analysis, then all of our variables are measured using standard deviation units. They all have the same scale. They all are scaled according to a z-score. So that's what we do with a standardized beta. And here's the original picture. And note that I've put this red ring around my x1 variable and my y variable on the left. And I put the term z-scores over here to clarify that is what we're turning into z-scores. And the key thing to note when you're doing multiple regression, the standardized beta is what you get if you turn everything to z-scores prior to analysis, before you do anything. So before I do anything, I first turn x1 into a z-score, and then I turn my outcome variable y into a z-score. And then once everything is z-scores, I use my control variable, comes along and munches up everything it can, it tries to explain all the variance it can explain. And then I have this leftover, the residual of x1 after the control variable is extracted out. That's the uniqueness of x1. And I have the uniqueness of y, everything that's extracted out of y after controlling for the control variable. Now note that in this example I started off where I turned everything to z-scores, and then I extracted out the uniqueness of x1. And I have everybody's new score on x1 with the control variable extracted out. And that new score on x1 is no longer a z-score. It's probably something pretty close to a z-score because I started off with z-scores. But I started off with z-scores, extract out the uniqueness, the stuff that can't be explained by the control variable, and these new scores on x1, people's scores with the control variable extracted out, these new scores are now going to no longer be z-scores. They'll be close to z-scores, but they won't be exactly z-scores anymore. And likewise, I turn everybody's score on y into a z-score, extract out the uniqueness of y, that's the stuff on y that can't be explained by the control variable, and everybody has a new score on y, your score on y, with the control variable extracted out. And again, that new score on y with the control variable extracted out, that uniqueness of y, is no longer a z-score. It'll probably be close to a z-score because I started off with z-scores, but once I extract the uniqueness out, once the control variable munches up and chews up and spits out or swallows or does whatever it does with that variance it's explaining, once I have that residual of y, that residual of y is no longer a z-score. And so then at this point I take this residual from x1 based on the standardized x1, and I take the residual for y based on the standardized y and use that residual of x1 to predict the residual of y, and that is my beta for a standardized beta. That's the beta for x1 if I'm calculating standardized betas. So the standardized beta is the beta you get if you're doing multiple regression and you turn all your variables into z-scores prior to analysis. A standardized beta is a resulting beta when all the variables are standardized prior to analysis. So if you extract your control variables out of x and get the uniqueness of x controlling for the control variables, and extract the control variables out of y and get the uniqueness of y controlling for the control variables, and then you use that uniqueness of x to predict the uniqueness of y, the resulting beta will be a standardized beta, assuming your very first step was to turn everything into z-scores prior to analysis. If you started off with z-scores, then those betas will be standardized betas. Now, note that the standardized beta is not the same thing as the correlation. In our previous unit, when we were doing simple regression, when I had just one predictor, if we turned that single predictor, if we turned that into a z-score and got a standardized beta for simple regression, that standardized beta was the same thing as a correlation. That's because when I'm doing simple regression with just one predictor, I'm not controlling for anything. Now, in multiple regression, when I have more than one predictor, each beta gives me the effect of that predictor controlling for all the other predictors in that equation, and the standardized beta will give me a standardized effect, the effect that I get if I turn all my variables to z-scores prior to analysis, which is helpful because now I can interpret everything in terms of a z-score scale. Everything now has the same measurement units. Everything is measured in standard deviation units. Now, note that a standardized beta, you can interpret that as being similar to a correlation in terms of what you might call a small, medium, or large effect. So its scale of a standardized beta will be somewhat similar to a correlation. So for example, if I had a standardized beta of 0.5, I might call that a large effect, and so forth. But it's not going to be exactly a correlation because a standardized beta, in this case, is not a correlation. And so, for example, a correlation mathematically can only range between 0 and +1 and 0 and -1, and it's not mathematically possible to get a correlation larger than 1. With a standardized beta, it will have a scale that ranges from about approximately in the range of +1 to 0 or -1 to 0, but not exactly that. So it's mathematically possible to actually run an equation and get a beta that's slightly larger than 1. Now, actually, if that happened, it would mean you've got some other problems in your equation. That's kind of an unusual situation that really only happens if you've got some problems in your variables, but it's mathematically possible to happen that way. So we can interpret the standardized beta in terms of what you would call a small, medium, or large effect. You can interpret it basically the same way you would interpret a correlation for what's small, medium, or large, because it's a very similar scale, but it's not precisely exactly the same scale as a correlation. And the key advantage we get when we calculate standardized betas is that now, because everything is measured using the same measurement units, because everything is now measured in standard deviation units, in z-scores, we can now compare the relative unique contribution of each variable in predicting an outcome. So let's see how that works out in our example. So recall I was using a person's income, how much money they make in a year, and the number of times a person smiled in 10 minutes. I was using income and smiles to predict how influential a person was. and we already looked at results for our unstandardized betas, and we saw that we had an intercept of 38.55, and the slope for income was a very small slope of 0.00007. The slope for smiles, our second beta, was 1.34. And as I talked about before, even though 0.00007 is a very small number, we can't interpret this effect for income being smaller than the effect for smiles because income and smiles are being measured using two different scales. The units of income are much smaller units than the units for smiles, so we can't compare these two numbers. And that's always true whenever you have unstandardized betas. You might have this beta might be larger, that one might be smaller, but you can't presume this is a bigger effect just because it's a bigger number. Now, when I turn everything into z-scores prior to analysis, now I can make that comparison because now everything is measured using the same scale. Everything is measured in standard deviation units. So we see that the standardized beta for income is 0.306. The standardized beta for smiles is a smaller standardized beta, 0.101, and now we can conclude that indeed it looks like we have a bigger effect for income and smiles is having a weaker effect. And this comparison is now meaningful because we're measuring everything in z-score units. Also, by the way, note that our intercept is going to be 0. And this was true in our unit on simple regression as well, that if you turn everything into z-scores, then your intercepts will always end up being 0, which is why we have an intercept of 0 in that equation. So the typical way of calculating a standardized beta is to do what we've been talking about. That is, you turn all your variables into z-scores prior to analysis, and then you run your multiple regression equation, and the beta weights from that multiple regression equation are standardized betas because you turn everything to z-scores prior to analysis. But there may be some situations where you encounter unstandardized betas, and you need to find some way to convert them into standardized betas. For example, maybe you're reading a journal article and the author of a research study has reported regression results, and for some reason that author has reported unstandardized betas, but that the study has used scales with arbitrary units, and you can't tell if those effect sizes are big or small because it's all unstandardized betas and you don't understand the units of analysis that were used on those scales. This actually happens quite frequently, even myself. There's many times where I'm actually reading a journal article and I encounter unstandardized betas, and I wish those authors would have reported standardized betas. It would have made it a whole lot easier for me to interpret those results. And so what I want to do is I want to take those unstandardized betas and standardize them myself so I can get a sense of what those results are. And here is a formula you can use to do that. And of course, another place where this formula might come in handy is if you happen to be taking a test in my class and I give you unstandardized betas and ask you to convert them to standardized betas. So this formula works well for that case as well. And it's a fairly simple formula. All you do is you take, if you want to calculate your standardized beta, you take your unstandardized beta from just a raw score regression equation. We're using raw scores without standardizing anything. So you take that unstandardized beta and multiply it by the standard deviation of x divided by the standard deviation of y, and that will turn your unstandardized raw score beta into a standardized beta. That simple formula will do that for you. So we've been talking about betas and standardized betas, and now I want to introduce a new thing, which is a partial correlation. The word partial comes from the idea of partialing, and we've actually been talking about partialing, although I haven't used that word. I've been using the word extraction. But when I've been talking about extracting one variable out of another way of saying the same thing is to partial one variable out of another. And so a partial correlation is a correlation where we've partialed one variable out of another. That is, where we have extracted one variable out of another. And a partial correlation is very, very, very similar to a standardized beta. It's just one subtle difference. Recall with the standardized beta, I first turned everything to z-scores before I did anything else. And then I extracted the uniqueness out of x and uniqueness out of y and used that uniqueness of x to predict the uniqueness of y. With a partial correlation, I'm going to switch the order of things. I'm going to first extract uniquenesses and then turn things into z-scores. So I start off at the top here with unstandardized x and unstandardized y. Nothing's a z-score yet. And I take my hungry frog control variable here. The control variable comes along and munches up, explains everything it can. And so now I've got the residual of x1, all that stuff on x1 that couldn't be explained by my control, and the residual of y, the stuff on y that couldn't be explained by the control. And so now everybody has a new score on x1, and everybody has a new score on y. And I'm going to take everybody's new score on x1, that residual, that score, that uniqueness score, your score on x1 that couldn't be explained by the control, and I'm going to take everyone's uniqueness on x1 and I'm going to turn that into z-scores. And then I'm going to take everyone's residual on y, that part on y that couldn't be explained by the control. That is, after I extract the control out of y, everybody has a new score on y that's your score on y with the control variable extracted out. And I'm going to take that new score and turn it into a z-score. So now at this point I have the z-scores for the residual of x1 and the z-scores for the residual of y. And I will use that z-score residual for x1 to predict the z-score residual for y, and the resulting beta will now be something I call a partial correlation. And it actually is a correlation. This is actually something that will have the same correlation scale. It will range from 0 to +1 or 0 to -1, just like a correlation. We can actually call this a correlation because it's actually looking at the effect between two things that are z-scores. How much does the z-score for the residual of x predict the z-score for the residual of y? And because I'm dealing with z-scores at this level, we can actually call this a type of correlation. Now this is not our regular bivariate correlation. This is a partial correlation that's giving us the effect of x1 on y with our control variable partialed out. That is, controlling for our control variable, or with our control variable extracted out of both x and y. So that will give us a partial correlation. Again, if I first extract my uniquenesses, if I first extract the residuals out of x, and then extract the residuals out of y, and then turn those residuals into z-scores, and then use the standardized residual of x to predict the standardized residual of y, that gives me a partial correlation. The beta weight I get from that simple regression equation is a beta weight I can call a partial correlation. Now, the formulas that are used to calculate a partial correlation can actually get really messy and complex. However, if you're doing a multiple regression equation, and if you've calculated your beta weights, just your unstandardized regular beta weights from a multiple regression equation, and then if you do a t-test to test the significance of your beta weight, actually we'll talk about that in just a moment here, if you do a t-test for your beta weights and take that t-value, you can actually take that t-value and convert it into a partial correlation. You can calculate what that partial correlation is if you have t-values using this formula I have right here on this page, right there. And if you look at that formula, you might get a bit of deja vu. Do you recall, where have you seen that formula before? That's the same formula I gave you when we were talking about making dichotomous contrasts. If I had, say, a treatment group and a control group, and I wanted to see if the mean for the treatment group was higher than the mean for the control group, and we talked about how the usual effect size we would use when doing group comparisons is a d-statistic, but an alternate effect size we could use would be a correlation. In that case, I called it the point by serial correlation if I wanted to give it a fancy name. And the formula I gave you for the point by serial correlation was this exact same formula right here, where I took the t-value, in that case from my contrast comparing my two groups. I got a t-test and got my t-value and plugged that into this formula here and got my point by serial correlation from that previous unit. Now I'm going to take that exact same formula and use it to calculate a partial correlation. This is actually a generic formula that essentially takes t-values and turns them into correlations. So if you take a t-value from a group contrast where you're comparing two groups and take that t-value and plug this formula in, that will give you an effect size for comparing those two groups, which is a point by serial correlation. And if you do a t-test for a beta weight and take the t-value you get from the beta weight and plug that in, which we're doing right here, then you will get a partial correlation, which is giving you the partial correlation using x to predict y and giving you the effect of x on y after controlling for the other control variables in your equation. That's what the partial correlation is giving you. So all you need to do is do your regular multiple regression. You'll get a beta weight and you'll get a t-value testing the significance of your beta weight. Take that t-value for the beta weight, plug it in there, t squared divided by that t squared plus your degrees of freedom. And your degrees of freedom, they're the same residual degrees of freedom we talked about earlier in this unit from that ANOVA table. It's your total sample size n minus number of predictors minus 1 and your degrees of freedom. And so if you get your t-value, your degrees of freedom, plug that in, and you will get your partial correlation. I have one thing to note here, is that this formula right here cannot possibly produce a negative value. And so it will actually, technically what this gives you is not actually your partial correlation, but the absolute value of your partial correlation. In other words, if you have a negative effect, if as one variable goes up, the other goes down, if your partial correlation is actually negative, this will still be a positive value. So what you need to do if you're going to use this formula, you need to look at the beta weight. And if that beta weight has a negative value, then you need to make your partial correlation negative. If the beta is positive, then leave your partial correlation positive. But if the beta is negative and you use this formula, then you need to add a negative sign to your partial correlation because your partial correlation should be negative as well. So that's a formula you can use if you need to calculate partial correlations. Now let's look at our example here and see how the unstandardized beta compares with the standardized beta. We've looked at that already, and how both of those compare now with the partial correlation. And if you look, the standardized beta and the partial correlation here, I got for income, the standardized beta was 0.306. The partial correlation I got was 0.308, which is very, very close. For smiles, I got 0.101 for my standardized beta and 0.106 for my partial correlation. And that is actually pretty typical. It is actually very common for your standardized beta and your partial correlation to be pretty close to the same thing. That is because it's a rather subtle difference between the two. It's just a matter of, are you going to standardize everything first and then extract your residuals? Or are you first going to extract your residuals and then standardize your residuals? Do you first extract, then standardize? Or do you first standardize, then extract? And the difference between those two things, if you're thinking, "Wow, that seems like a subtle difference," well, yeah, it is. It doesn't, more often than not, you would not get a big difference between those two. And if I was reporting results in a journal article or a paper, I wouldn't report both standardized betas and partial correlations because they're so close to each other, it's essentially redundant information. Now, that raises a question, so which one should you use? And on one hand, there's really no right or wrong answer to that. But for this class, let's make the default that if I don't say anything, standardized betas will be the thing to report. So if you're doing a multiple regression, and I want you to report results for how much each x variable explains variance in an outcome after controlling for other variables in the equation, if I don't say anything else, the default will always be to report a standardized beta, and only report partial correlations or unstandardized betas, only report those other options if I specifically ask for them. So the default will be report standardized betas. On the one hand, partial correlations do have an advantage over a standardized beta because a partial correlation actually is a correlation, and you can interpret a partial correlation on a scale that is exactly from 0 to +1 to 0 to -1, whereas a standardized beta actually isn't technically a correlation, and the scale isn't exactly from 0 to +1 to 0 to -1. So on one hand, you might think that a partial correlation might be better than a standardized beta because its scale actually is a correlation scale. On the other hand, if you look at statistics and think about more advanced statistics and all the different types of things that you might calculate if you go on, for example, going on and doing things we call path analysis, the standardized betas have much broader, wider use. There are many, many situations where you can use standardized betas where you can't use partial correlations. And there's many situations where it's very easy just to turn everything to z-scores and get results, where trying to calculate partial correlations becomes very cumbersome and complex. And so a standardized beta is something that's much more practical than a partial correlation. And for that reason, they're much more popular. So if you look at journal articles, you're much more likely to see people reporting standardized betas. Partial correlations are much rarer, less common to report, partly because standardized betas just are applicable to so many different situations above and beyond even what we're talking about here. So because standardized betas, if you go out in the real world, because standardized betas are probably the most common standardized results to report, we'll make that the default for what you report in this class as well. With that being said, note that because a partial correlation actually is a correlation, it also means we can square it, and that will be the percent of variance explained. We can't do that with raw score betas, and we can't do that with standardized betas. We can't square them and have percent of variance explained. But a partial correlation is something we can take a partial correlation and square it, and that will be the percent of variance explained. And so if we want to look at our Venn diagrams here and talk about percent of variance explained, well, this is a place where the partial correlations we can plug those in really easily. So we can say our squared partial correlation, the percent of variance explained, is for a partial correlation is this area B divided by area A plus B. And note that area A plus B, that's the total variance of Y after x2 has been extracted out of it. So it's the residual variance in Y after x2 is extracted out. And so this area B is the part of the residual variance of Y that's been explained by the residual variance of x1. And that's what the partial correlation squared tells us. What is the percent of variance in the residual of y that's explained by the residual of x after x2, after the control variable, has been extracted out of everything. And so then if we simply take the square root of our partial correlation squared, the square root of area B divided by area A plus B will give us the partial correlation. So we can use the Venn diagram to directly represent partial correlations and partial correlations squared. Now, if we do want to use a Venn diagram to talk about betas or standardized betas, we can note that for betas and standardized betas, as well as for partial correlations, for all three of these statistics, we're all looking at area B in our Venn diagram. These are all different ways of talking about how big is area B, what size of an effect that is. In other words, they're all answering the same question, which is, what is the effect of X predicting Y after controlling for the other variables in our equation? To what extent does X explain variance in Y after controlling for the other variables in our equation? And area B is giving us that effect. So we can say that the beta is giving us information about the size of area B, and likewise, a standardized beta is also giving us information about the size of area B, and we could even add that it's giving us information about the size of area B when everything has been turned to z-scores prior to analysis. In other words, everything has a standard deviation of 1, which means they all have a variance of 1. So the standard deviation is 1, so the square standard deviation is also 1, the variance of y is 1, the variance of x is 1. All these have standard deviations and variances equal to 1. So we can say that the beta tells us about the size of area B. Using a Venn diagram, we can't say much else than that, but we can say at least it tells us about the size of area B. The standardized beta also tells us about the size of area B, and does so when everything is turned to z-scores prior to analysis. And the partial correlation tells us specifically about the size of area B in terms of how much variance in the residual of y has been explained by the residual of x1. Area B divided by a plus b, and take the square root, you have your partial correlation. Or if we don't take the square root, we have our squared partial correlation, the percent of variance explained. So in that way, we could probably, in some ways, talk about betas, standardized betas, and partial correlations. They all refer to area B in our Venn diagram. So the beta, the standardized beta, and the partial correlation are all doing the same thing. All three of those statistics are effect sizes giving you the effect of X in predicting an outcome variable Y after controlling for all the other variables in the equation. They're all three different ways of talking about the exact same effect size. What's the effect of x on y controlling for the other variables in the equation? Now, recall that we've been going through three different big questions in this unit. We talked about what's the effect of each x variable on y, ignoring the other variables in the equation. What is the effect of all of our x variables taken together? And now, what's the effect of each x variable controlling for the other variables in the equation? And in each situation, we looked at two specific questions. That is, we wanted to look at two types of statistics. What statistic gives you an effect size for describing the strength or magnitude of relationship that you're looking at? And second, what is an inferential statistic that you can use to test the significance of that effect? So the beta, the standardized beta, and the partial correlation, all three of those are effect sizes. They're all ways of describing the effect of x on y controlling for the other variables in the equation. And like I said, for this class, if I don't specify, the default effect size will be to report a standardized beta. You could report a beta, although those are often hard to interpret, and you could report a partial correlation, but it's more common to report a standardized beta, and that will be the default for this class. So if that's an effect size, if betas, standardized betas, and partial correlations are all effect sizes, how do you test the significance of that test? And we will test the significance with a t-test. So the t-test will be our inferential statistic. And as always, a t-test is always where you take a statistic divided by its standard error. So if I want to get the t-value for my beta weight, I just take my beta weight divided by its standard error. And I could give you a formula for that, although for our unit on multiple regression, I'm not going to bother with that. It gets a bit complex and I want to move on to other things, so we'll just let the computer output calculate our standard errors for us. That is, if you do your study over and over again, how much will your beta typically deviate from that true population parameter? That's the standard error of your beta. And so we'll let the computer calculate that for us. And then we'll take our beta divided by its standard error, and we'll get a t-value. And as always, once we have a t-value, we can determine the probability of our result if the null hypothesis is true. And as always, to determine the probability of a t-value, we need to know what our t-value is, and we need to know degrees of freedom. And our degrees of freedom are the same residual error degrees of freedom we've seen previously in this unit. If you recall back from that ANOVA table we looked at, it was your sample size n minus number of predictors, p's number of predictors, minus 1, and that will be your degrees of freedom. So if you have your t-value, degrees of freedom, you could use a t-table or go online, find a t-calculator, or use a computer and calculate the probability of your beta if the null what's the probability of getting this result if the null hypothesis were true. And as always, if your probability is less than 0.05, you would call your result significant and reject the null hypothesis and claim that your beta is not 0, that the true population parameter is something other than 0. In other words, you claim you have discovered a non-zero effect. So because a beta and a standardized beta and a partial correlation are just three different ways of measuring the same effect, your t-value for a beta will be the same as the t-value you get if you calculate a standardized beta and calculate the t-test for that. And that would be the same as the t-test you get if you calculate a t-value for a partial correlation. And to save us work, I'm not going to go through giving you separate formulas for each of these because they would all produce the exact same result. And that's actually what people typically do in real life. Typically, if you're doing research and you want to test the significance, I would just use a t-test for my regular unstandardized beta. And once I get that t-value and I get my probability of that t, I know that that t and that p-value will be the same for my beta, for my unstandardized beta, and for my partial correlation, so I don't bother to calculate other t-values or other probability values because I know it will all be the same thing. I just calculate my t-value and my probability for my unstandardized beta, and then I stop there because I know it will be the same if I standardize things or if I calculate partial correlations. So that is how you would test the significance of your beta or your standardized beta or your partial correlation. So to summarize, we've been looking at these three different questions we can address when we do multiple regression. We have one question, which is, what is the effect of each x variable on an outcome, ignoring the other predictors? We have another question that is, what is the effect of all of our predictors taken together in predicting an outcome, and a third question, which is what is the effect of each variable after controlling for the others. And for each of these three questions, we looked at two different statistics. We looked at what is the effect size that gives us information about the magnitude of effect. And secondly, we looked at what is the inferential statistic that we can use to test the significance of our effect size. So when we ask the question, what is the effect of each variable ignoring the others, our effect size was our lowercase r, a simple bivariate correlation. Or we could square that correlation and get lowercase r squared, but the default and the more common thing is to report the unsquared lowercase correlation. And then what did we use to test the significance of our correlation? We tested the significance of our correlation with a t-test. And then the second question, what is the effect of all the variables taken together? Our effect size there, in this case we usually square it, is the uppercase multiple correlation, capital R squared, the percent of variance explained, is a typical statistic to report for an effect size, although we could also report the unsquared version of the multiple correlation, but it's much more common, and the default for this class is to report the effect size, which is capital R squared, the multiple correlation squared. And what do we use to test the significance of our capital R squared? We test the significance of our multiple correlation, or multiple correlation squared, with an F-test. So the F-test, the ANOVA, the analysis of variance, and the F value we get from doing an analysis of variance is how we test the significance of our capital R squared. And then we were looking at what's the effect of each x variable controlling for the others. We saw that we can use a beta, a standardized beta, or a partial correlation, and we test the significance of that with a t-test. Again, and note, I've talked before about the difference between focus and omnibus questions. Note that both the simple bivariate correlation and the beta is a focused question. You're looking with the, in the first case, what is the effect of each variable on an outcome ignoring the others? I have one x and one y. It says, what's the effect of this x on y ignoring the others? Or with a beta, standardized beta partial correlation, what's the effect of this x on y controlling for the others? But I'm still focused on a question of what's the relationship between x and y, two variables, something I can hold in two hands. So both the bivariate correlation and the betas, standardized betas, partial correlations, these are all focused questions so that we test significance with a t-test. With a correlation, it's a correlation divided by its standard error. Beta is the beta divided by its standard error. So it's two different t-tests that are measuring two different effects, but in both cases it's a t-test, a statistic divided by its standard error. Whereas the multiple correlation, we've got more than two variables involved. We have what is the total effect of all my predictors taken together, and I could have 2, 3, 4, 5 different predictors and an outcome, more things than I can hold in two hands, so my significance test will be based on an F statistic and not a T. So that's all the stuff we've talked about up to this point. And actually, I've got one more statistic, one more way that we can actually look at what is the effect of each x variable controlling for the others. That's actually going to be partly a focused question, then it's going to kind of morph into an omnibus question eventually. So I've got one more thing I want to talk about here, and I'm going to save that for the next video. So at this point, we have covered everything for up through Unit 5C, up through Part C for Unit 5.